Okay, part one, chapter four. Let's see. So, share screen. One. Okay, so energy of life. Okay, so all cells capture and use energy. Okay, so you know, in science we have a very precise definition of energy. Okay, energy is the ability to do work, to move things around. Those things can be small, like photons, or those things can be big, like mountains. But either way, energy is the ability to do work, and that means, in our case, to move. Okay. Okay. Energy has two different forms. Okay, kinetic energy and potential energy. Kinetic energy is the energy of movement. Okay, potential energy is the energy of position. Okay, so if you're moving, you have kinetic energy. Okay, if you're not moving, you have no potential, no kinetic energy. Okay, potential energy is stored energy. It's the energy of position. Okay, like on top of this hill right here, this dude has really high potential energy. And since he's not moving, or like, before he starts riding down the hill, he's not moving, he has no kinetic energy. Okay. As he starts down the hill, he is transforming the potential energy into kinetic energy. Okay. Um, here is a compressed spring. A compressed spring consists of high potential energy. There's energy in the position that it's in. Okay. When it recoils, when it springs, okay, the kinetic energy of the spring is translated into the potential energy of the ball. Okay. So now the ball can be transformed into kinetic energy. And so that kinetic energy can make the ball go up. Okay. Okay. So chemical bonds or potential energy. So this is chemical bonds like sugar have a lot of potential energy in them. So if I take up sugar, I can break it, okay, into little pieces, and every time I break it, I release energy. Okay, and two options: to capture the energy or to not capture the energy. If I don't capture the energy, it's released as it's lost as heat. If I can capture the energy, I can use it to power things. And so we do that. Okay. Okay. Energy is converted from one form to another. So energy changes within this biological system. Energy is never created or destroyed according to what's known as the first law of thermodynamics. Okay. So the first law of thermodynamics is that energy is never created or destroyed. Okay. Therefore, the first, like, you only translate from kinetic energy to potential energy, and ultimately, every step of the process, a little bit of it is used released as heat energy. Okay, but that heat energy is going to be constant, so the heat energy is going to steadily increase. Okay. Okay. Cells are able to use chemical energy. So energy from the sun cannot directly be used by the cells. Okay. We can't, like, it's not like a solar power flashlight. Um, so the kinetic energy must be captured, stored, and converted before it's usable for cellular work. And that is what we will cover in the next two chapters. Okay. Okay, so energy transformations are inefficient. Okay, at every single step, a little bit of heat energy is lost. Okay, heat energy, in other terms, is this ordered form of energy, which means it cannot be used or converted back to a more useful form. Okay, so slowly we're losing energy to heat. Okay. Okay. Energy input is required for life on Earth. So it takes a lot of energy to stay ordered. Okay. The cells constantly use energy to build their molecules and structures, perform chemical reactions, and stuff like that. And all these processes require energy. And most of the energy comes ultimately from sunlight. Okay. The kinetic energy of the light. Okay. Okay. So sunlight is kinetic energy. Kinetic energy powers this process called photosynthesis. Photosynthesis makes stores energy as potential energy. So it takes CO2 and makes sugars out of them. So we're storing the energy from sunlight in forms of potential energy. Okay, the potential energy of sugar. Okay, and there's cellular respiration. We burn that chemical, burn the sugar, and we use that as uh, chemical energy for available for cellular tasks and kinetic energy for movement. Okay, and so it all goes through a nice little circle. Okay, but at every step of the way, you have output as heat energy, and the only input is sunlight. Okay, so sunlight produces almost all our energy. Okay. Okay. The second term that you have to understand is chaos and entropy. Okay. Entropy is a measure of disorder. Okay. Um, so the randomness of the universe can be described as disorder or entropy. Since heat energy is going to be constantly lost in the universe, and heat as energy is disordered, the entropy of the universe is by definition increasing. Okay, this is the second law of thermodynamics. Okay, the second law of thermodynamics states that for every reaction, entropy is always increasing. Okay, so think of your room for a second. Okay, your room, if you don't. Okay, so imagine your room for a second. Okay, your room is, if you leave it alone, if you just try to function in there, it'll get more and more disorganized. Okay, so entropy increases. It takes a lot of energy to organize your room. Okay, so it the entropy of the universe is increased when you organize your room. The entropy of your room decreases. Okay. All right. So this will be part of your homework. So make sure you know how to use the following terms. Okay. Okay. Metabolism. Okay. It includes all the chemical reactions inside the body. Okay. Their chemical reactions can be split into two groups: building stuff and breaking stuff. Okay. Building complex molecules. Okay. Requires energy, and that is called anabolism. Okay. Taking things and breaking them apart is catabolism. Okay. And that usually releases energy. Okay. 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 One of the more unique forms of energy transfer is called oxidation reduction reactions. Okay. Remember electrons from chapter 2? Electrons are on the outer shells. They can be transferred from one atom to another or one molecule to another. And electrons contain energy. Okay. Um, so when you lose electrons, this is oxidation. When you gain electrons, it's called reduction. So these things always happen together. So something always loses electrons, something always gains them. Okay, so the term, the easy way to remember is oil rig. Okay, oxidation is the loss of electrons, reduction is the gain of electrons. Okay, now I'll explain the concept there, I'll explain the next couple of slides. Electrons contain energy. Okay, electrons are always moving, so they contain energy. So if I lose electrons, I lose that energy. If I gain electrons, I pick up that energy. Okay. All right. So, okay, the reduced molecule gains energy, the oxidized molecule loses the energy. Okay, and this doesn't happen independently; they always happen together. So one thing is oxidized and one thing is reduced. Okay, so as you go down the electron transport chain, I am reducing this. Okay, I'm oxidizing A. So imagine this being called A. B, C, D, E. Okay, so A is currently reduced, okay, because it has electrons. I'm going to oxidize A and reduce B, okay, at the same time. And then I'm going to oxidize B and reduce C at the same time. And then I'm going to oxidize C and reduce D, okay, and so on and so forth. Okay, so you just keep moving it down the chain. Okay, that thing is called electron transport chain. Okay, and an electron transport chain is like a molecular game of hot potatoes. Okay, you just pass it on down the chain. Okay. Okay, photosynthesis and cellular respiration both use electron transport chains. So we will cover it in more detail in the next two chapters. Okay, so okay, to pass electrons down a chain. Okay, so okay, as you move through the electron transport chain, molecule X is transferring the electron to molecule Y. So as molecule X is being oxidized, okay, molecule Y is being reduced. Okay. I think they have that backwards. Okay. So why are they always this? Okay, good. All right. ATP is the energy currency of the cell. Okay. I'm sure you guys know this already. So ATP, okay, is the energy currency. So this is what ATP looks like. These bonds, these wiggly lines are high energy bonds. So if I break them, okay, I can release a lot of energy all at one time. Okay. So I break it, I release energy. Okay. And when I have extra energy, I can add the bond back, and that is ATP synthesis, and I can store energy. Okay. Okay. So I can use energy by breaking the bond, I can store energy by making it. Okay. Okay. ATP hydrolysis can energize molecules. So if I want to take ATP, I can use one of the phosphates, put it onto another group, like this sugar right here, and the sugar right there, then it becomes energized. And I can use that to power things down the line. Okay, so like This is energized, so I can form a bond right here easily. Okay. We'll talk about this later in the chapter, but this ATP can be used to add phosphate groups to other molecules, and then I can change the shape of the molecules and make them do different things. Okay. What is most likely coupled with hydrolysis at ATP? So when I want to break ATP, hydrolysis is the breaking of ATP. Okay, I will use it to build stuff. So A is building stuff. So A is correct. B is actually breaking down stuff. So that usually gets your ATP, not breaks up ATP. Joining monosaccharides together builds stuff. Okay, so A and C are correct. All right. Oh. Okay, so that ends this part right here.